some homeworks too. What did you do yesterday? Okay, yeah. That's good. You don't have to do anything, something. Okay, so the door was open, was it? The door, was the door open?
Oh,
The
yeah,
front door.
there was like a paper.
Yeah, I think that. Take that. Okay. All right, getting ready. Christine and Anna is coming today. So yeah, you guys see her when she comes in. Did you have any questions from the homework?
I had some.
Okay, let's go through that as we have a bit of time. Okay. What are they?
It's like question 19A.
19. Oh, yeah. Don't worry about it for now. Okay. We haven't done the Bose model. Like I gave you like total collection of everything. So.
Oh, okay. Is that the same as question 23?
I guess so. It's in the same category. Yeah, 23. Yeah. Okay. Good question. But yeah, something. Just leave that for now, and we're probably covering the Bose and Schrödinger's model next week. Or likely next week. So yeah. So when we're covering that, then I'll explain you how to think about like excited state and Bose model, maybe some of the Schrödinger's model too. And that's end of the chapter 1. It's a module 1. Yeah. So that's the end. This is the end actually.
Oh.
Yeah.
How about question 25A?
Okay. Identify the particles represented X and Y and Z. So what you have to look at it is from the previous 239 to 94 PU. Where's my pen? Okay. It'll be something about like it's about the radioactivity. So 239, 40, 94. That is PU plus X. They're making that 240, 94 PU plus Y is making that 241, 94. That's PU again too. So what you see there is it's increasing the number of the mass number only without touching that number of the atomic number. So you got to think of like a bit like simple mathematics in here that if you want to ignore the Y, if you want to make the 240.94 from 239.94, that means X must be something like 1 and 0. Okay, then and consider about what would be a particle that carries the mass but does not carry any charges or the atomic number. It has it's a mass number 1, but no charge. Or it has the same mass number as proton, but it does not have any charge. Oh, it would be neutron.
Oh.
Okay, this is the no charge is the key to explain or understand the question that we have 94 to 94 doesn't really change the atomic number at all too. But think about it here. Atomic number stands for the number of the protons and number of the electrons only. As we do not have any change in atomic number, and since we have a change in the mass number there, it must be neutron. Okay, it'll be the same for the Y. Okay, the Y does not really change the atomic number either too, so it'll be 1, 0 neutron as well. And eventually it goes through the some sort of the nuclear. Yeah, it'll be something like that 241, 94, americium, and that is now produced. Comparing to 241.94 to 241.94, so 95, I'm sorry, 95. Hello, Anna. Hi. Okay. Okay. Having like looking at the difference between these two over here, then you to see, oh, there's no change. So let's go like this. Like as I said, it's kind of more like a simple mathematics that there's no change in the mass number, so it'll be 0. But what I see is I see some changes in that 94 to 95. So just considering this like mathematical equations, to make it that is true, it would be -1. That must be -1. And something that carries the -1 charge by having 0 mass number is electron or the beta particles. Okay, we didn't really talk about the neutron because it's more related to physics. This is known as the nuclear fission or artificial like nucleosynthesis. So, but that's the food for thought. And smoke detector, americium 21 slowly changes the Neptune 237, right, a balance. So I finished that B as well too. So we have a 241.95 americium. Now turns it into the Neptune 237. So we have 237. Hello, Christine. 237. Atomic number of the two. What is that? Neptune. Neptune is, where is Neptune? Yep. NP. Okay. Is known as the 93. Like that over here. Okay. Where are you up to? Like up to?
I'm about like half, 3/4, I think it is.
3/4?
Ish.
And do it now. Okay.
Oh, I did it for
Oh yeah. Oh yeah. All right. Okay. All right. So let us think of like a 241 to 237, 95 to 93. As I said, like just do a simple math. Just 241 minus 237 gives you something like 4. 95 minus 93 gives you 2. So something that carries the mass number of the 4, atomic number of 2, which means this has 2 protons and 2 neutrons. It just simply be what? Helium, alpha particles like this. Okay. Do not get afraid of any of those we call like a nucleosynthesis or the radioactive decay series, because even though you get something out of what we learned, that is alpha, beta, and gamma particles, if you could do just like a little simple mathematics, like simple calculation that, oh, I'm minusing these same mass number to the atomic numbers, then we get some values too. And you just need to determine that what would be the possible particles that we can have. Yes, we may get some neutrons, which is quite unusual. This is not a decay, by the way. That's more like a nuclear fusion. So the fusion reaction. This is question 25 of your homework, holiday homework. Okay. I got the book here. Oh, thank you. Oh, thank you. So I got a book, and today, many of people still in holiday, so they'll probably join us like after a few weeks. I don't know when they're gonna join, but it is what it is. All right, what we're going to go through today is, first, we're gonna revise that's where we're up to from. Not everything, but mainly about like something in terms of the balanced electrons. We talked about bondings last time, so it might be a good chance to like talk about like revising the bondings as well too, because I know you learned bondings from since when? Since like year 9, but it is very important. Oh, biology. Okay, let's leave that for now. So we're going to spend about like an hour, like 40 minutes to about like some revising some of the contents we learned. When we're describing the chemistry, like when the description of the chemistry, or assume that we have a chemical, it could be any of the chemicals too. We have a couple of ways to describing that what the chemical is. So just checking. Yeah. That we can describe the chemical as in like how they look like. How they look like. Or I call the structure of the chemicals. Or I can describe that as chemicals as in like what they are made of. What they are made of. So that is the compositions. So when I'm talking about like what the structure of the chemicals or anything, we have three typical structures. One is we call it atomic structure. Second is molecular structure. Third is lattice structure. We only have three. That atomic structure is something look like this. We have a single atoms. That is not really, remember that there's no chemical bonding. No chemical bonding at all. So it just comes as it is, like just one single thing. Molecular, it has the chemical bonding. So what we see that is a couple, or some are joint, maybe with the different like colors of that. Goes like this, or even goes like up to maybe more, even further, like up to goes like this. Okay, that's how we describe that as, oh, this is known as the molecular structure. So when you see the when you like heard, like you see read the molecules, it's basically describing about how they look like. They look like, oh, we have a bonded something. I have a few things here. It look like this. These are the molecules basically. Okay, just think that as, oh, I think simply as, oh, these are what they look like. Lattice is something that more in complex in a network. That is, it could be in like this, some forming some sort of the building structures. Even further, like it goes further, so it kind of stretched it. Okay, that's called the lattice structures we're describing in chemistry. Now, when we then classify or like categorize chemicals in terms of their composition, what they're made of, we can talk about in terms of these first. I need to use black. Okay. Okay. First, we can talk about they're in the element. Okay, and second in compound. I'm talking about just the pure substances. There is something that made with the pure mix of the pure substance known as the mixture. And in the mixtures we have homogeneous and heterogeneous. So I'm not going to talk more about the mixture, basically just briefly, but let's focus more on the element and the compound then. Element, when we say, oh, you probably heard, like as you heard, or like you've probably read that, like, oh, we have a few elements. Element simply means that single, or like it's just one type of the chemicals only. So, for example, I have like hydrogen. It's only one type we have. If we like let's say like we have in space, they only have a hydrogen. I would say, oh, that's a hydrogen element there. Okay. If I started having something mixed, that would no longer be an element. That would be a mixture. If, for example, air is the mixture of the hydrogen, oxygen, argon, some other gases too. So I can't say there's a hydrogen gas only here. It's on one type only. So O2, even carbon, something like, I don't know, ions, many others. Compounds would be two or more. Joint. Or they bonded. Okay, for example, CO2 is known as the compound. Sodium chloride, NaCl, is also known as the compound too, because they're made with the sodium and chloride, which is quite a different like atoms, joint in the chemical bondings, and this is why we call it compound. And in many cases, you may get confused about compound and molecules, because some texts kind of mix use that. Oh, we have a compound, we have a sodium chloride compound. Sometimes we say we have sodium chloride molecules, water compounds, water molecules too. But the way we have to differentiate that is molecules specifically talking about how they look like. okay? Which means we got to think about the relation in here. For the elements, when we have purely elements, okay? Christine, can we have elements in atomic structure? Yeah, can we have element in molecular structure? Okay, can you give me an example of the atomic elements atomic structure then? Just O, but can we have the O as just the O? Because the non-metals more like it comes in diatomic, but it's close. What about group 18? Helium, neon, group 1, that's group 1. Helium, neon, in the morning, understand, okay? Helium, neon, argon, which are known as noble gases, they don't really need to combine. They don't need to be bonded to. So this is the type of when we only have the helium gas, that is the helium element atomic structure. Does it make sense? Okay. So it will have comes in the single forms with a single type only. Element in molecular structures, it'll be O2. That is a joint. So something look like this. It's a joint. It's bonded, but I only have same type of that element. Okay. What about element in lattice? Can we have the element lattice? Elements in the lattice, like a network of the same type? Yes, we can. We talked about the iron or the metals, like all the metals within the metallic metallic bondings. We have a lattice structures too. Carbon have the lattice structure we know as a covalent lattice structures too. It will only consist of the one type of the element, which is a carbon. Does it make sense? Okay. And actually, can we then have compounds in atomic structure? No. Why is that? Why can't we have compound in atomic structure then? Yeah, two of it must be bonded. But as soon as we say, oh, they must be bonded to get the to fulfill the definition of the compound, but atomic structure means that they're not bonded at all too. So we cannot have compound in atomic structure. So we never say that we have oxygen the helium compound or the argon compound in this reason why. Okay, but we can have many of the compounds in molecular structures. Okay. Anna, can you give me one example? Compounds in molecular structures? CO2, it's given here. Okay, one more. Maybe, that depends. I'm looking for something that's very common. Very common. There we go. This is a typical example of the compound in molecular structure. Okay, what about compound in lattice structure? Can we have two or more joint to form the building block or the network? We can. This is sodium chloride, more likely. Okay, as we learned that ionic bonding is forming like a joint, two ions, many ions join to make the network. That's a lattice structures too. Now, the reason why I'm bringing up the structures again too is this is the key to understand the states in the room temperature. In every single time, most of the time when we have atomic structures, okay, so I mean, for example, like all the noble gases there, that comes in the gaseous state. And the reason is very simple. When they're not very bounded, they're quite light, kind of free to move around. And as we learned about the energy, they have lots of energy. They can flee a lot, free like if they just fly away easily. For the molecular structures, most of the time they comes out in the forms of gas too, but depends. If they have some strong bonding between two molecules, many of the molecules, that comes out the state of the liquid. So water is a good example. It comes in the molecular compound, but it comes as liquid. CO2, however, comes in a gaseous state. Okay, lattice. I discussed quite a lot about the lattice before too. Every single time you have a lattice, doesn't matter what makes a lattice, what doesn't matter the composition of the lattice, they are almost like comes in the state of this solid at room temperature. For example, metals, except the mercury, metals comes in the solid state. Okay, sodium chloride, salt, ion lattice comes in the solid state. Lattice made with the carbons, that's what? That's basically graphite and diamonds that we discussed before too, allotropes. So be sure that you know what kind of structures they have, because later on when we're starting learning about module 2, I'm not too sure whether you learned about how to state. We did that in year 10 before too, but you gotta learn about, you need to state the chemicals without told, like, that's like a solid, liquid, or aqueous. Okay, so I'm giving a little hint that most of the cases, atomic gas, molecular gas, or liquid, that is just be a solid too. Any questions up to here? Okay. All right, talking about a little bit of mixture, we have two types of mixtures, as homogeneous or heterogeneous. Homogeneous means that that's evenly, uniformly mixed, like air we're having now. If I take the air sample from the top and the bottom, I'm expecting that they're pretty much having the same composition in terms of same percentage too. So that's how we call it homogeneous. Or another good example is your soft drink, soda water. Okay, drinking top of the water, bottom of the different drinks, bottle, you get the same taste basically. Okay, heterogeneous means that something that unevenly mixed. That you can talk about some of the pebbles under the water. Okay, that's a mixture, but that's something that not uniformly mixed. And we discussed, and we actually performed the prac that how to separate the mixture. So Christine, what's the key to separating? Doesn't really matter homogeneous, heterogeneous. What's the key to separate the mixture? Yeah, what should we do? Like, what do we use to separate the mixture? So, for example, we have salt water again. What did we use? We use boiling point. What's the category of the boiling point? That's called using the physical properties. So by using there are different type of physical properties, we are able to separate the mixture. So good example is, as you said, boiling point or the melting point sometimes too, but we're more likely using the boiling point. That salt and the water mixture can be separated, separated by using, we basically boil that salt water. And depends on what we aim to get. If you want to get this salt left over, that's called evaporation. Technique called evaporation. But if you want to get the water out of the salt water, that's called a distillations. So that's related to the technique called the evaporation or the distillation. Remember that evaporation has the purpose of collecting the solid. Distillation more like collecting the water, like a liquid in that case. Anything else? We went through many. Ashley, what was the other type of physical properties that we used to separate the mixture that we had? We used the size. Do you remember the techniques that relate to size? Sieving. Anything else? Depends on state as well too. We use the filtration. But simply means a water molecule has a smaller size than the other pebbles and solid, so that it comes straight down. So we can filtrate it using the size and sometimes mix with the density. Okay, too. So density is something also using. If you have an oil and water mixture, we're using something known as the separating phenol. Okay, so what we do, we put that in the separating phenol. We know that oil is less dense than the water, so we just turn the tap on, get the water out, and leave the oils only. That's how we can separate them too, using the density differences too. What if we have metals? What if we have metals? Then we're using something known as the magnetism. That metals tends to be attracted to the magnets. So what we do, we had some nuts, the metal nuts. So we use the method of hovering around to remove all the metals out. That's what we can do as well too. We can also use the rule called the solubility. That the property of it can be dissolved or not dissolved in the water. So probably you're given the mixture of the salt, not the salt water. So first thing you probably did was you mix that into you put everything into the water with the sand and pebbles, because we know that salt will dissolve in the water, but not the pebbles. So using the solubility, so that's basically dissolve and what we do is a filtrate, we are able to separate some of the mixtures too. Now, there are many other like mixtures too, like some centrifugations too, but we don't really use that in the school lab. But we commonly use in the laboratory that separating a different like if you want to get the plasma from your blood samples too, we use that because they have the same different densities too. There are various. So most likely when you go back to school in term 1 in a few weeks, you are performing some sort of like separating the mixture prac. Okay. You might get a report writing about it. There's a few schools who had like they had like a report writing about the separating the mixtures, but just be aware of that. It's always about the physical property differences. Okay, if you can figure out the physical property difference between two mixture or two chemicals, you should be able to separate them according to that physical property. So these are the typical physical properties too, and I'll probably give you some questions about it too in your homework, and you will get those questions probably again in your topic test or module test later on too. Any question? This is end of chapter 1. Done. Okay. We talked about some of like percentage and other calculations too, but let's skip that. I want to focus more on to the chemical property then. Okay. I hope you remember that when we have, so I'm going to skip some electron configuration, the way we can fill it up the electrons, because we're coming back to the electron configuration again once we're starting learning about Schrodinger's and Bohr's model too. And I'll probably ask you to leave that now because I want to finish up the Schrodinger's model so that we can get the right electron configuration of the Bohr's model too. It's actually really simple once you understand that, but if you try to read the textbook, it's really complicated because they're using some of the quantum physics to explain that terms. I'm not going to use any quantum physics. I'm just going to use the periodic table to explain that. Okay, so we kind of discussed that when an element, remember that I'm talking about element, just a single type. When an element has the valence electron that's less than 4, okay, that means according to remember this, the octet rule, they would have a tendency of losing electron. Okay, this is categorized as we know as a metal in chemistry. Now, when the valence electron is greater than 4, okay, let's skip the equals to 4. They have a tendency of the gaining electron, and they would have the non-categorized as non-metals. When the valence electron is equals to 4, that's known as they have a tendency of the sharing electron, or they can lose and they gain the same time, sharing or losing even plus the gaining in the same time. That's known as the metalloid, sometimes known as the semi-metal. Exception is the carbon, that is a non-metal. So as I said, we are studying carbon chemistry separately because it is so special. It has a strong property of the sharing the electrons. That is called the organic chemistry. Okay, let's do this one too. When the valence electron is equals to 8, which is the fulfilling all the octet rules, that's known as the noble gas, which means they will not be reacting. So also known as inert or non-reactive gases because they have a full shell. Okay, so quickly talk about some trends on the periodic table using this. I'm going to spend not too much time on this, okay? I'll ask you to memorize not the trends, but the reasoning for why we get the trends, okay? So we have two trends going down a group across the period. So let's go one by one. Down a group. Christy, what's happening when we're going down a group? What's happening to those elements, the chemicals, when we're going down a group? Yeah, but I mean there are too many. Okay, just imagine about we're going down a group. What's happening in terms of the number of the shells? Yeah, the shell number is increased. Okay, the number of the shell is increased. So this kind of explains everything about the trends we discussed too, including the atomic radius or atomic size. What else? Electronegativity, first ionizing energy, even for like some reactivity as well too. Okay, what about across the period? Yes, I'll ask you to memorize the term, the fancy term, that what happens to these elements going across the period. That is the getting the stronger electrostatic attraction or force of attraction. Same word, attraction towards to the nucleus. Simply means that everything goes, the force or the attraction towards the nucleus is getting bigger. And down the group means that size is getting bigger like this. And this explains you everything about the trends, including the atomic radius. So what happens to atomic radius as you're going down the groups? As the number of the shells increase, obviously it gets increased. See, this is why I never ask you to memorize the trends, but if you understand the reason why, what happens as you're going down the group across the period, you don't really need to memorize them. It just comes naturally. Across the period, as we're getting stronger attraction towards the nucleus, and what happens to the atomic radius then? It decreases too, because they're shrinking down the size. We also discuss about electronegativity. We're going to talk about the electronegativity more today, later on too. Electronegativity means that a tendency of gaining electron. High electronegativity means that they have more tendency, they're willing to gain more electrons more and more. So down the group, the shell size getting increased, or like we have a greater size, that it will be harder to gain the electron, means that it will be decreased. Okay. Across the period, what happened as we're shrinking down, size getting smaller, so it means that we have more positivity kind of approaching to, so it'll be increased. First, ionization energy, in short IE, I just write that as, okay? As the size getting bigger down the group, okay? What does it mean by the first ionization energy actually?
The amount of energy to
remove the first ion, or required to remove the first ion here. Okay, so it means that in a situation where if the atom or the element wants to gain in a situation, it means that it will be harder to remove the electron from it. So it shares the same trends as electronegativity, in other words. So size getting bigger as going down the groups, therefore it takes the less amount of energy to remove the first electrons, that is decreased. Across the period again, size is getting smaller, more positivity. It'll be harder. If you imagine about two magnets really close together, you kind of detach them, it's harder. So it means that that'll be increased in first ionization energy. And for this type of question here, we discussed about the trends. Do you remember the this kind of like the graph questions that we have? I showed you before too. Yeah, that is something that you have to consider as well too. Then you might give it a graph of something, then ask you to like just saying analyze the graph or analyze the trends in that graph. That's basically the same as like this trendy question too. Okay, everyone good up to this point? Okay, core charge. What is core charge? Core charge means that the total number of the protons minus the inner shell electron. So for example, sodium. Sodium has atomic number of the 11 atomic number. Now, the reason why we say inner shell electron is we do not care about the valence electron. Okay, so if sodium has 11 total number of the 11 electrons, it has one valence electron. So what would be the inner shell electron number? That would be 10. Inner shell isn't like it fills at first and second shell, it has only one. So we don't care about valence shell in this case and gives you +1. Chlorine. Chlorine has the atomic number of the 17. Okay. Anna, what would be the number of the inner shell electron for chlorine then? If the chlorine is the same period, it would be 10. So it gives you what? Plus 7. So it tells you that, oh, greater the core charge, and you can just kind of think the deal same as the electronegativity. It means that carrying the great positivity in the inside, tendency of the gaining electron would be increased in this case. So as we're going across the period, the core charge is getting increased. Sorry, down at the down the group, going across the period, increased. Okay, I give you an example. Sodium has core charge of 1, chlorine has core charge of 7. But what about we have something like potassium, say like lithium? Lithium has atomic number of 3. Okay, total number of 3 means that it filled inner shell 2 and leaving the 1 out. When you calculate the core charge, we don't really care about like a valence electron. So that means it'll be -2. Gives you what? +1. But what we see there is sodium and lithium both have the same core charges. So in terms of the core charge on the down the group, there'll be no change. Okay, let's do 2 more. Okay, what about metal reactivity? Actually, what does it mean by metal reactivity? When I say not just simply reactivity, when I just say like metal reactivity, tended to lose electron, because remember that metal is the one that always want to lose electron. So greater the metal reactivity means that they have a more tendency of losing electron. Does it make sense? So you can just write it as tendency of losing electron in this case. Then Christine, what do you think about the trends of the metal reactivity as we're going down the group? Would it be increased? Why? You're right. Why? The shell numbers increased, therefore, what happened? As the shell number is getting increased, do you think it would be easier or harder to lose? It would be easier to lose an electron. That's all you need to say. It doesn't matter what trends you're asked. I just want to use that reasoning to back it up, saying that, yes, metal reactivity getting increased as it goes down the group, because the size of the shell, size of the atoms get a big increase due to the greater number of the shell numbers. Therefore, it'll be easier to lose electron. Okay. What about across the period? Size is getting smaller, it's more shrinking down, which means that it's getting harder to lose an electron. So metal reactivity getting decreased. Is that true? Yes. If you're thinking about groups, group 1 is known that as they're having the greatest tendency of losing electron, followed by group 2, and these on the left-hand side, yes, it goes like in losing that tendency of losing electron. Okay, we also have something known as non-metal reactivity. Do not confuse these 2 points over here. The reason why I don't like to use the word reactivity in chemistry is because we have a few different chemicals and very distinctive chemical properties. That metal reactivity tells you the tendency of losing electron, which means that non-metal reactivity tells you that tendency of gaining electron. But did we talk about the tendency of gaining electron before? This is same as almost like the electronegativity then. Okay, which means it will share the same trend as electronegativity, that going down the group as the size is getting bigger, it'll be harder to gain, so it'll be decreased in terms of the non-metal reactivity. Also, across the period, it will get increased. Does it make sense? So this is the reason why we found that as you're going down, or even for the halogens, group 17, okay, they will have the lower non-metal reactivity or lower electronegativity than before. So this is the trends that we talked about last time, okay, and yes, you will definitely get questions about it. And then we also discussed about type of bonding. Let's go quickly on the different type of bondings and move on to the VSEPR theory. So type of bondings can be decided by what chemicals are joined together. Yes? Yeah, quickly. Okay. I need to continue on though. Okay. We have some situation that we have metals plus metals. Okay. When you're talking about the bondings, you simply need to thinking about the chemical property of the metals that has less than 4 valence electrons. So we discussed that these are the one that I just go quickly on this tossing the electrons. None of those metals would like to gain the electrons, so what they do, they're kind of tossing the electrons away. This seems like a very similar scene as like playing the volleyballs, that we're playing the volleyballs to each other. And it's kind of funny thing that this gives very special features of the bondings. We call the bonding called the metallic bonding. That's in between the C of the localized electrons. That's also known as a free electrons, and the metal ion lattice structure. Okay, so the common type of question you get is relate that to its metal's physical property then. First, we talked about like many of the physical properties. Metals are have a tendency, or like they are, I should write it in black. Metal physical property. And what are some of the metal's typical physical properties? There comes in solids at room temperature. Yeah, and high density. More. High melting. What about boiling point? Both melting and boiling point. Very good. Give me one more. Malleable. Maybe one more. Ductile. Thank you. It comes together. Malleable, and ductile. Also good electric and thermal conductor. Okay, and once you know all, you can just use your like assume that you have a piece of metals in front of you, to thinking about the property of that too. So because physical properties are basically something you can see in macroscopic levels without doing any chemical experiment. Understanding this physical properties, you just simply relate that to its structure or the chemical property. That why is it solid? Because in the lattice structure. Okay, why does it have a high density? Same reason, because in the lattice structure means that they're in the network. We discussed that before. High melting and boiling point. Okay, something having high melting and boiling point means that the bonding between the metals are so strong. So boiling, think about it, the word of the melting and boiling means that from the solid it's really kind of dense. Okay, we give a heat to separate them. Liquid would be some moderate separation, but gas would be quite wide separation. So that's also because of the metal ions kind of bounded really strongly too. Malleable ductility, this is a very special feature of the metals that I hope you remember that what happens to the metal ions, they can slide to each other. Because as we are playing volleyballs, they are kind of not fixed. They are quite flexible in terms of, but not flexible as in like they can go further. They can slide side to by side, up and down. So that is metal ions, lattice structures, malleability, ductility gives you the reason why that gives the rationale. Electric and thermal conductivity. Okay, that's all because of the C of the delocalized electrons. That electrons are free. Okay, many, like most of all of those electrons are free. So when we plug that the really positive, super positive, electron will jump towards that. That's known as the electricity or electric conductivity. Thermal conductivity, shake or bivariation, is quite free. Even for both of the metal ions and the localized electron too, they are easy to be vibrated because they are not fixed. It's quite flexible. So you can imagine about the kind of a liquid like jelly shape. When we tremble that, you can see like good vibration of that too. That's basically the same thing happens in metals too. All right, ionic bondings from metals plus non-metals. Okay, in this case, what they do, they are transferring. Not tossing, transferring as in like they permanently give away the electron and permanently receive the electron. So as a result of that, they're forming some metals, right here. Metal becomes 2, the positively charged cation. Non-metal becomes 2, the negatively charged anion. And because we have a positive and negative, and opposite attracts according to like a nature of the law, these two will join to form something known as the ionic bonding. So for example, we can have sodium chloride always in the solid state. Because we have a many ions there, they are more likely to form excuse me, they will likely form that ionic lattice structure. So considering that they are having ionic lattice structures there, it gives us their typical physical property as well, just straight away. So type of physical property of the metal and non-metals. First, they're in the solid because in the lattice structure at room temperature 25 degrees Celsius. Sodium chloride, solid. Remember that I'm going to talk about the molten and dissolved salt as well too. But solid, that means that it's kind of it's basically table salt. So I hope you remember the table salt. And what happened to the lattice structures too? They would have that quite not really high density. They're good solid, maybe soluble, something that different to the metal. Okay, but that still carries the high melting point, even for the boiling point too. But we probably don't consider a boiling point because realistically we don't get the boiling gaseous sodium chloride. Okay. Are they malleable or ductile? No. Unlike the metallic lattice structures too, they are not really able to like slide to each other. So what happens is when we hammer them, we basically shatters and breaks the salt. We can make the thin wires of the salt either too. In this reason why. Okay, so you must know the difference between ionic lattice to the metallic lattice. Even further for the covalent lattice later on. Are they in the good electric conductivity? No, they are poor electric and thermal conductivity. And why is that then? Why is it something that's very important? Because you would get the questions about it. The reason why ionic lattice structures or sodium chloride solid would not have a good electric conductivity is simply they do not have free electrons or free ions available. Conversely, saying, then if they have free ions, if they have free electrons, they will be most likely good at conducting the electricity and the heat as well too. So that is the main difference between sodium chloride liquid and sodium chloride aqueous. Okay, solid is basically solid. Liquid is known as molten salt. Sodium chloride aqueous, as you can see, AQ stands for the aqua, which is water. This is dissolved salt. Okay, I hope you can spot out the difference between molten and dissolved salt in here. Molten simply means we give it lots of heat. So maybe, for example, we give it up to 600 degrees Celsius of the heat to make it solid salt into the liquefied kind of liquid. You can think of like a magma, like a lava kind of salt there. So that's a salt, even though like that's in the liquid state. Dissolved salt is much easier to make. That basically puts the water to dissolve it. So as I explained, I show you the diagram here that molten salt is actually look like this. If we have a sodium and chloride would be just separated as it is. So we have separated sodium chloride from the lattice structures. So what are the structure of these? They're most likely coming in the atomic or even for the molecular structures in this case. Okay. Now, sodium chloride aqueous means it looked like this. The sodium is surrounded by the water molecules, so that is oxygen surrounding that. So water molecules are helping the sodium and chloride to be separated, because we're going to talk about some of the more intermolecular forces, but these water, each of the water molecules carries a bit of known as the partial charges. So as you can see, like they are being separated, again, separated by the water, help of the water. This is help of the heat. But regardless of what they look like, we know the similarity between these molten and dissolved salt, that the ions now separated. Ions are now free. So I don't think that people will never do that for the molten salt because it goes up to 600 degrees Celsius, but technically and theoretically, they are able to conduct the electricity. In fact, they're really good conductor. So good example is salt water, seawater. If you put the electrode into the salt water, seawater there too, you're expecting that there are good flows of electricity. You may get the electric shock as well too. Okay, but for the rock salt, they do not. This is a typical type of exam question that you can get. They're asking you, why would molten and dissolved salt conduct the electricity well in the same time lattice sodium chloride solid would not? Okay, to explain that question, to explain the answer for the question, you need to know the main difference between the state, what makes a difference to, and you also need to know what does it mean by the good electric conductivity. Remember that good electric conductivity means that the good flows of the either the ions or the electrons. The last thing we discussed before you go to holiday last year, it was about metals, non-metals, and non-metal combination. That is known as the they are basically sharing the electron because none of those would like to lose, they would like to gain the electron. So that's known as the covalent bonding. Okay, covalent bonding is something that's very special because depends on the it is the one that can have up to single, double, triple, depends on how many have there in the vacancies. So for this type of here, we will get the most likely get the molecular structures. But sometimes we can also get in the lattice structures too. So let's talk about covalent bonding in molecular structures. Examples are they? We have O2, H2, N2. So as you can see, the non-metals are highly reactive in terms of the gaining electrons. So they cannot come as a single non-metals. They form something known as diatomic molecular structure of the non-metal element. And this is the reason why I explained you, re-explained you about element and molecular so that you can differentiate what I mean by here. When I'm saying diatomic means made with the two. Molecular, as you know, they're joined with the chemical bondings. Element means just pure things, okay? We have some exception of the H2O. This is the what? Some molecular structure of the compound. Molecular compound. So sometimes we describe the compound, molecular compound, when we say molecular compounds, because think about it here. Can we get molecular compound in metals and non-metals? Would they have like some molecular compound? I mean, they'll be in compound, but it's hard to attain that molecular structure in the ionic bondings. It's either be like all separated or all joined. Can we get molecular compound in metallic structures? Can we get them? First of all, can we get molecules in metals? In other words, did you see like, except the mercury, probably mercury is a good example, but did you ever see like gases, metal? If you're seeing that, like you're probably under the near at the inner core of this under our Earth, there's iron core. That's more like a gaseous ion than that too. So it requires quite a lot of heat. So I'm talking about like an everyday life at 25 degrees Celsius. So when we say molecular compounds a lot, this is more likely meaning that covalent bonding structures. Because simply we cannot have this one from the ionic bonding. We cannot have from the metals easily. Okay. So H2 of that too, and this explains you there are many of the physical property again too, that these are not solid, they're more like comes in the gases or liquid. Okay. Also, there comes into the pretty low boiling point and melting point. It comes in the gas and liquid form too. What about their conductivity? They would have, okay, they're not having any free electrons nor the free ions, so they'll have a poor electric conductivity as well too. Lattice structure in the covalent bonding is, for example, probably the best example is the carbons. So let's talk about it's a physical property of that. I can actually write it down, physical properties. First of all, when the carbons or the non-metals are forming the lattice structures, we name that as covalent lattice structure. It would have the solid state. Yes, obviously, because in the lattice structures at room temperature. So a good example of that is graphite or the diamonds, or the covalent lattice structures made with the carbons. Solid, relatively high boiling point, melting, and the boiling point as well too. It's all due to that shape of the structure. What else? Would that have the good electric conductivity? Maybe. Okay, graphite has the good electric conductivity, or like not that good, moderate electric conductivity. Has some, or sometimes actually good, because graphites actually look like, when you're seeing like a shape of the graphite, they look like this, the layers of carbons, whereas diamonds were like a complex, and they are kind of joined inside here like that. Okay, so having the layers carbon means that we have at the edge, there will be some electrons are available. Electrons from the unjoined bondings too. So these electrons are quite free. That means that when we try to conduct electricity from the graphite, they can conduct the electricity pretty well. And we actually use that in the industrial side quite a lot for the graphite. In other words, when you plug that, your lead, pencil lead, okay, it actually can conduct the electricity. Diamonds, however, as all the bondings are formed, so none of those carbons are missing the bonding electrons to form the bonding. Means that there's no free electron again, so it would have the poor electric conductivity. Diamonds are known to be reflective, therefore it's quite expensive. Not quite, it is expensive. Okay, 1 carat costs like $5,000, something like that too. Yeah, okay, that's a reality of the boys, by the way. I've always been saying that too. 5,000, good money. All right, maybe more by the time you get married. Okay, so diamonds are quite expensive because they're reflective. Because what they do when the light comes in, they captures the light inside. Okay, so and then kind of reflect it back. So you see that depends on the angles of the diamond. Like you see shine, you see the different colors of that too, because lights get reflected and then gets shown the different colors. Okay, but for the graphite, if you think about it here, because they have a layers of the carbons, when the light comes in, they get captured inside of the layers. They can easily get captured. Some of the sometimes it's kind of reflective. It's more, but this is why graphite comes in the color of the black, because it captures all that light. The way we can think about it is the reason why the black hole has a black hole, because black hole is the one that like capturing all the lights in, so that it's not really black, but it shows the color of the we describe that as black color as absorbing all the colors or absorbing all the light. Okay, the relation between these two, as you can see, they have the same chemical compositions, with the different the physical structure. We name that as allotropes. Do not mix use that with the isotopes, by the way. Okay, I saw some test papers say, oh, after that saying that this is isotope. I'm like, no, no. Isotope is what? Having the same atomic number with a different mass number. So if the person got confused about same and different too. It simply means having the same chemical compositions, but because they have a different physical structures, they will carry the very different distinctive physical properties as well too. Just like a graphite and diamonds in this case. Makes sense? I tried to cover all that year 11, more than half of the year 11 module 1 content. Now it's been an hour. Done. Any questions up to here? Okay. So before we move to the best fit theory, I know it's quite tiring. There's a huge amount of information just in 1 hour to let's have a short break. Okay. We're going to come back for the chapter 4 today. So let's start with chapter 6, which is on your page 209, please. I'm going to introduce something known as the VSEPR theory, but I know the spelling is VSEPR, so valence shell electron pair repulsion. But simply thinking like we just pronounce it as a VSEPR theory. This is the one that explaining you what the shape of the molecular compound. Remember that this is only for the molecular, more likely molecular compounds. Okay, means that I'm talking about more likely the covalent molecules in this case here. So again, covalent molecule means they have non-metals and non-metal combinations. So the things that you have to remember is that the simple rule is this: electrons are something known as negatively charged particle. That's electron, how we define the electrons, okay? Which means that when we have electrons too, like I'm putting the electrons in the closed position together, they will repel. So repulsion in between electrons, because opposites attract, the same side will repel. That's a simple rule. And what we do using is we're using that simple rule to describe that why the shape of the certain thing, the chemicals or compounds look like that. And for that, there's a few rules. I mean, this is kind of really complicated explanation, to be honest, too. So I'll kind of short it down. I can make a summary of that. Or I give you some shortcut. All right, guys, you need to memorize a few things and for this to get the to solve the question, to be honest. Okay, one, memorize some fundamental. The shape. Okay, that when we have two attached, the shape in the fundamental shape is known as linear. When we have three attached, the fundamental is known as the trigonal planar. When we have four attached, that's fundamental known as tetrahedral. So I show you that what I mean by linear. This is a linear. How? Yes, linear. Done. Okay, that's what the linear look like. They're simply connecting by two, having a linear shape. That's a two. Okay. Trigonal planar is somewhat. Do I have that here? No, I don't. Okay. Oh, yeah. Do some. Need to use this. Trigonal planar is this. Okay. Or it's not trigonal. Trigonal planar. That is in the plane. It's not in the shape of 3D. It's in plane that having the three all together. So I draw that as 1, 2, and 3. Linear. Let's go like this. Okay. Tetrahedral is something that can new terms that it look like this. It's easy to show like from this one here. This is known as the tetrahedral shape. That you see that from the center atom, when the four things attached, are going like this, okay, it makes the shape of that tetrahedral shape. And this is known as the basic or the fundamental shape. The second rule is that you always focus on the center atoms. So every single time we have a molecules, we say we have a center. This is a center of that. Okay, what you see there is you're seeing that the center now has 4 attachments. Okay, so it depends on the attachment you have. It will decide that what type of the fundamental shape they will have. The third is when we have something known as lone pair. Lone pair is considered as an attachment. For example, assume that I have this kind of shape. Did I have that from the previous class? I believe I left that. Nope. I should like this. This is easier. Assume that we have 3 attachments, okay, but one having the lone pair. The lone pair means, the way you can think about it is, lone pair is the pair of the unshared electrons. So for example, if I ask you to draw the NH3 in the Lewis, let's take this a Lewis structure, then you probably learned that nitrogen has 5 valence electrons, so it can share up to 3. So you will share 1, 2, and 3, and then leaving that 2 electrons on the top. I'm talking, this is your lone pair, also known as lonely pairs that's not belonging to anywhere. Okay, so we take the lone pair as our attachment, but as you can see, it doesn't really like in a change in the structure whatsoever too. So this is something that considered to be attachment, but it's not really, it's a kind of invisible attachment in this case. Okay, this is something like a rules that you need to remember to do the VSEPR theory. Then, without telling you like explain everything in here, I explain you why that H2O. Okay, let's give us some example of that H2O and maybe the CO2, the shape of that. So to do those, you should be able to draw a Lewis dot structure or Lewis structure. Remember that Lewis dot structure means that you need to represent the covalent bonding in the dots. Lewis structure means you can represent the covalent bonding in the lines. So let's draw that H2O. Anna, what would be the center atom between H2O in the H2O? O is your center atom. Okay, now let's draw that. Hydrogen can share up to just 1 valence electron. So it will share an electron like this in the Lewis structure. Oh, in the Lewis dot, I show you that it'll be like this. Okay, now remember that, or using your periodic table, you know that oxygen has 6 valence electron, means that only 2 can involve in the covalent bondings. Rest of the 4 will left as the lone pairs. So what that means is we get the lone pairs on the top, even for both of that. Does it make sense? Okay, then what you start to see here is just count for how many attachments that oxygen has, which is the center atom has. Oxygen here now has 1, 2, and remember that we're taking the lone pair as the attachment to 3 and 4. Okay, so it has 4 attachments. But what we see there is 2 are the lone pairs. So this is what happened then. I have 4 attachments. As you can see, I have 4 attachments. This is not really oxygen there. I have 4 attachments there, but lone pair is something that is not really involved to form the atom. So what they do is, I'm taking this off, 1 and 2. Then you start to see the shape of the bend. Okay, so this is how we can figure out, oh, because we have a 4 in a the basic shape of the tetrahedral, okay, because 2 of those are the lone pairs, we're kind of removing that and leaving the structure. And now this is showing you a bent structure. So this is a modification from the fundamental shape. That is now known as the bent shape. Okay, so always start from the fundamental or the basic shape, and then if you get rid of those, can you see that the bent shape is formed? Okay, all right, what about CO2? Let's draw that. Carbon dioxide would have the carbon is your central atom this time too. Carbon can form up to 4 covalent bonds. Then it will form the 2 double bonds with the 2 oxygens like this. Yes, we have some lone pairs on the oxygen side there. But I don't care about the lone pairs and there's some attachments. What I only concern about the central atom. Does it make sense? Okay. So how many attachments How many attachments in this case? So that's kind of bent, okay? Christine, how many attachments in like carbons attached? There are 2. There's only 2 oxygens attached. Well, we don't count here. I'm only looking at the carbon. Double bonds are still the same as a single 2 in this case. We're only looking at the how many are attached. So I only say 2. The 2 attachments. Then what's the basic shape of the 2 attachments? That's the linear. This is the reason why H2O is a bend shape and CO2 is the linear shape. Okay, I'm not going to explain you like why they're doing that or what kind of repulsion theory too. Again, that's too complicated. So I'm just what I'm giving you is this is the technique that we're using in the chemistry Olympiad too. That so solving the question quite easily. Yes.
So are the workers only counted as attachments
in the middle, in the center only. Okay, shall we do some more? Okay, can I delete that? What about PCl3? So I believe we have some examples given here. So let's have a look at that. The page. Screen 218, please. pH3. Sorry, there's pH3. Could you do the 2 questions? Okay, first start with the Lewis dot structures or Lewis structures, and give it a go. We gotta go through the answers together then. And actually, can I get your homework on the holiday? Yeah. Yeah, cheers, thank you. It's okay. Yeah, there you go. I only have one. Okay. If you're not too sure about like how many covalent bonding can be formed, you can look up the periodic tables if you need one. Yeah. Glad that you always get this in your exam too. But it's good to memorize some of the common non-metals. That phosphorus is group. What's the group? This group 16. It's the same group in the nitrogen. So P. Yeah, during the phosphorus itself, it will have the 5 valence electron like that. Okay, so let's draw that in the Lewis dot structures. Then hydrogen will form the bonding like this. Okay, this is a Lewis dot structure. Lewis structure would be that. Remember that if the question asks you to draw the Lewis dot, you must draw the Lewis dot only, no lines. But Lewis structure means you can show the covalent bonding in the lines like this. So how many attachments then? What we see there is, we're seeing that this phosphorus is attached to 1, 2, 3, 4. So 4 attachments. With the 1 lone pair. Then this is somewhat look like this. 4 attachments. I'll show you that. We have 4 attachments, which is a basic shape of the tetrahedral. From the tetrahedral shape, if we remove 1, because this one is a lone pair, it shows you some sort of a triangle. But unlike the, remember that trigonal planar was something that is like a plane. It would like a flat. But this is like a 3D shape, like a pyramid. So what we call that shape is, this is known as triagonal pyramidal. The shape. And this is how the pyramidal shape look, like a pyramidal shape, like a pyramidal shape look like. Can you see that? Okay. It's also described in the previous page, that pyramidal shape. That I think that's better diagram than mine. That's what I mean, planar pyramidal shape like that. Okay. Trigonal bipyramidal, so that's something that was out of the syllabus, to be honest. But all right, what about H2S? I'm going to give you a few more. Draw the NH3, CH4. What else can we have? CCl4. COOH. PCl5. And not really. PCl5. Yeah, okay. PCl3 and PCl5 too. Okay, so to determine that, start with the Lewis or Lewis dot structures. That sulfur, what group is sulfur is? Same group as the oxygen, which is group 16, okay? Which means it has how many valence electrons? Having 6. So thinking about that, this is what you need to think, consider here. 6 valence electron means that according to octet rule, it can fill it up, making up to 2 covalent bondings. The sulfur can make up to 2 covalent bonding. So each bonding with the hydrogens, like this too, okay? And because the sulfur only have some few electrons, it will leave those lone pairs. We'll be going up and down like this. Then we just need to consider about the number of the attachments. So we have 4 attachments, okay? But 2 of those are lone pairs. What that means is it will leave that structure of those hydrogens, but lone pair would be kind of disappeared. So the shape that we have, the basic shape of the having 4 is tetrahedral. Removing 2 of the tetrahedral shape would be look like a bent shape. Okay, that's how we can deal with those, like the Bedford theory, the shape of the molecular compounds. Okay, I would like to try for these given over here. I'll give you about 5 minutes for these. COH, actually, let's write that here. CH3, COH, known as acetic acid. Actually, I'll leave that for the last. CH3, COH. 2 more minutes. So this will be your quick guideline to deal with the end of the VSEPR theory. That you first start with to draw a Lewis dot or Lewis structure, and you show every lone pairs, including all the central atoms out of 2, because that's including the Lewis structures too. 3, determine the number of the attachment to the central atoms. We only concern about the atom in the center, so we do not really concern about outside. Okay. 4, using the fundamental shape that I explained you to. So remember that 2 is the linear, 3 is a trigonal planar, and 4 is the tetrahedral. These shapes, if you have all the attachments filled, I mean, it's just simply following the fundamental shape. But you have a lone pairs, we kind of deduct that, so you can imagine about the shape. But guys, there are only few, up to 5 or 6, that you just need to imagine, and you can picture that. There won't be like hundreds of this shape. So that's a simple rules. They can deal with the Lewis structure then. All right, let's go for some of the go through that together. So nitrogen with the hydrogen, so that's known as NH3. Okay, I actually need to do the NH4. I show you that in a second. So nitrogen is in your using your periodic tables, or you just need to just know that from your experience. Nitrogen is a group 15, which means nitrogen itself can have up to 5 valence electrons, like this. It will form the covalent bonding with the 3 hydrogens in the form the Lewis dot structure look like this. There's a Lewis dot, and the Lewis structure would be something in the lines, but let's skip that for now. So after that, you just need to determine the number of the attachments that we have. 1, 2, 3, 4. Make sure you include the lone pair as your attachment as well. It means 4 attachments is basic shape or fundamental shape of tetrahedral. But as we're having 1 lone pair, eliminating 1 on the top, this will give you something known as trigonal pyramidal. Okay, so 4 attachments and 1 lone pair. Okay, let's do the CH4 carbon. How many covalent bonding does carbon have? It has 1, 2, 3, 4 like this. So this is kind of the tip to draw the Lewis dot structure as well too. Start off with showing the central atoms, like the number the valence electrons, and what you just need to show that is showing them in attachments, and use X to represent this covalent bonding. That's it. Okay. So carbon in the center now has how many? 1, 2, 3, 4 all together. So 4 attachments. Any lone pair? No. So this is tetrahedral then straight away. It is that easy once you understand, like, you get the method of it too. Without explaining you why we would get the tetrahedral shape. It's all about like it kind of repelling each other to make it even angles in any of the directions too. But that's something required to understand the orbitals in the Schrödinger's model. And I'm not going to go through too much detail about it, to be honest, because you won't get this question again in year 12. You only get that in maybe if you have one, the first assessment in term 1 and the yearly exam, only 2. So you just need to practice the how to get the figures to, and it will only be a 1 or 2 marks only. Okay. CCl4 again, carbon 1, 2, 3, 4, and it will have the 4 covalent bonding with a 4 chloride. Show that. But make sure you show all the relevant lone pairs, even though this is outside of the central atom, which means you need to show that all the chlorine or chloride now have this much of the lone pairs because they've now filled the full shell. Okay, it looks complicated, but the way you can draw the Lewis dot is pretty simple if you understand that. Then we have in the central atom carbon has 4 attachments. It doesn't really matter for like they have many lone pairs. I don't care. It only has 4. No lone pair means tetrahedral. Straight away. VSEPR. Okay, where is boron? Where can we find the boron from in the periodic table? What group? Boron is group 15. Sorry, 13. So it has how many? It has 1, 2, and 3. Boron is tend to known as the metal. So yeah, you might be questioning that, isn't that forming some sort of like ionic bonding too? But when it comes with the chloride, it's actually sharing the electrons too. So what that means is it will share the electron with the 3 chlorines, show the bondings. Okay, if you're sick of like drawing the X's, you can use a dot. Why not? This represents the Lewis dot structure of the boron tetrachloride. Okay, then how many attachments? 3. Any lone pair? None. Which means this will show the basic shape of the trigonal planar. Okay, the boron central atom doesn't have any lone pair in this case. PCl3. Okay, phosphorus has how many electrons? It has 5. So you show that. And Cl would be just go like this, and the X. Let's show that. Oh, XX then. Okay, so how many attachments? 4. And the lone pair, 1. So from the basic shape of 4, which is tetrahedral, having lone pair, this shows the, again, trigonal pyramidal. So you must spot the difference between trigonal planar to the trigonal pyramidal there too. Pyramidal shape is a kind of pyramidal shape, like real like a pyramid. Planar is plane. That's where the planet comes from. What about this one, PCl5? Okay, let's draw that. Phosphorus has 5 valence electrons. If all of those electrons get shared, and this is kind of odd situations too. We don't really get that a lot because by sharing the 5, all of the 5, it will now have more than 8 valence electrons. So there's known to be like a kind of temporary chemicals. What they do is share the electron with the chlorine, like this. Okay, the rest would be becomes to just lone pairs. And the Lewis structure in this case. Okay, now we haven't learned about 5, did we? Heavy. Okay, so having the 5 all together, it's good to know that they will form some of the 3 on the top and 2 on the top when it comes out. So from the tetrahedral shape, it has a 1 extra. So what they make is, it's actually shown on the page here, page 211. Having 5 attachment, it's known as trigonal bipyramidal. That having the 1 pyramid on the top and second pyramid at the bottom too. So that's what they look like. But this is kind of, we don't really get the many in many situations too. So I'm just giving you, in case you get the really difficult question about VSEPR theory. Okay. What about this? CH3COH. This is known as the acetic acid or acetate plus the hydrogen. So let's draw that. I'm running out of space, so I'll use this space for the acetic acid. When you're drawing that, CH, the carbon in the center, would form the, COOH part. Okay, this is a bit of a module 7 in year 12, but they sometimes use that to introduce, so it's good to know. COOH is known to be a carbonyl group, so we have double bonded oxygen with the OH is attached like this, and we have CH3. So I showed the CH3 as well part. CH3 would be carbon with the 3 hydrogens like that. So this is a CH3, there's a COOH. Okay? Now just have a look at this carbon. We have a carbon number 1, carbon number 2. I'm going to look at the carbon number 1 in here. See that this carbon now has how many attachments? 4 or 3? This carbon number 1. How many attachments? 3. Because we do not care about how many covalent bonding, single, double. I just simply think, it has 1, 2, and 3. Doesn't matter for CH3. It's a Berkey. I don't care. I'm just looking at this is attached with the 3 attachments. So having 3 attachments for carbon number 1, this means basic shape of the trigonal planar shape is given. Okay. Now, what about this one? What about for in this carbon 2's perspective? This carbon 2 has, see that? It has carbon 2 has 1, 2, 3 hydrogens attached with 1 Berkey COOH attached to. Okay, I don't care like what they are attached with. I'm only concerned about how many attachments they have now. So can you see like that 1, 2, 3, 4 attachments? So carbon 2 has 4 attachments without any lone pair. That means it would have the tetrahedral shape. Does it make sense to you? This is somewhat we're using the organic chemistry later on in the module 7. I'm gonna explain that a little bit about like the VSEPR theory, but we don't have much time to explain the VSEPR theory anymore too. Sometimes, it's one of the silicon schools trial papers. They ask you to think about what type of shape they have in the organic in this kind of compounds and how they decide their property as well too. Okay, so generally speaking, that if we have something shape of that trigonal planar or like some of that, we're gonna looking for whether they are symmetrical or asymmetrical. So thinking of the meaning of the symmetrical means that it's like a mirror image. So for example, if we have when I have a linear shape, saying a linear of something, CO2 for example. Okay, when I cut that in horizontal or the vertical there too, you will see that it will show the mirror image. Okay, then in this case, I call this is a symmetrical. What about for the essence? What about for the trigonal planar? Okay, would this be asymmetrical? It would not really be symmetrical because yes, it would be symmetrical for the vertical, but it would not really symmetrical for on this side there too. So in that case with asymmetrical, we tend to say they could carry some partial charges because they are not really balanced. They're not really balanced in this case. So that's maybe asymmetrical. Then what about tetrahedral shape? Tetrahedral shape is known as the typical symmetrical shape. That even we cut like this side, and that side, because it kind of evenly distributed, like it evenly dispersed, it will be symmetrical shape. Actually, this might be the symmetrical as well too, but compare that to the band shape. Band is a typical example of the asymmetrical. Because what you see there is, yes, it might be symmetrical in the vertically, but it would not be symmetrical in the horizontally. Another thing is we have a trigonal pyramidals. That's trigonal pyramidals. This is also known to be asymmetrical. So in the case of we have asymmetrical shape, we tend to say they are carrying some sort of the polarity, like positive and negative, because they are asymmetrical as in like unbalanced. They're not the mirror image. But when they're symmetrical, they're known to be a non-polar. So another way we can describe the shape in the VSEPR theory is we can describe that as some of those shapes are symmetrical, therefore symmetrical as in non-polar. They're not carrying any charges. For asymmetrical shape, however, carrying some charges like a polar charges. So this is a polar charge. There's a non-polar. This is a polar, sorry, as well too. So what you see there is the basic shapes, fundamental shapes I described. They are more likely asymmetrical, or exactly this one. Okay, so that's something that introducing known as the inter and intramolecular forces. So page 122, please. Let's talk more about some inter and intramolecular forces. So page 219 first of all. So this is the chapter that will bother you, with harassing you, until you finish your HSC. I must say that, because you will see the intramolecular, especially intermolecular forces a lot in Module 7, Module 8, Module 6, in the year 12 too. And if you don't have the good understanding about intermolecular forces from year 11, it will just keep left as a question mark. So every single time you see the intermolecular force, if you don't have good understanding in year 12, they'll be like, oh, this again. Oh. And you got to waste your time because you need to revise it back, but you don't really get the essence. So try your best. It's got to take a little while to understand some of the contents too, but try your best to understand and get the gist of the intramolecular forces today, maybe up to next week. Okay. So when we say inter and intra, the things that we have to remember is, in terms of the literal meaning, that intra is something happening inside. And inter, meaning that in between. Ooh, okay. What that means is intra. Okay, think about the example of that is internet. You guys know what the internet is? Yeah, you guys using the internet every night. Even now, I'm using the internet. I'm streaming this video. I'm using the internet. Okay, intranet. Have you ever heard about intranet? Okay, where do we use the word when do we use intranet or to the internet? Christy, when do we use the word? When did you heard when you use the word intranet? In the schools, we schools say a school intranet. For the staff members, for the students, we use an intranet, not the internet. When we say internet, however, I mean like in something outside of school. It can go anywhere. So what that means is, when we say intranet, it's an inside network. Okay, network inside your schools. They only get accessed by the people inside. But for the internet, it doesn't matter for who's coming in. It's general, you see a Google, that's internet. For international, even that too. Inter, in between the national. Where do we use the intra in the chemistry then? We're using that for intramolecular forces, or the interaction. It's kind of funny to say interaction to the in-between. So let's think about it here. When we say intramolecular, it means inside the molecules. Inside the molecules. So molecule as in some molecular shape, molecular structures too. It could be some covalent, some other things too. But we learned that intramolecular forces. What are the examples of the intra? Something happened inside the molecules. This is simply talking about the type of bondings they have. What type of bondings? We learned at least 3 types of bondings. 1, metallic. Yep. 2, ionic. 3, covalent. It's simply talking about those 3 bondings. Okay. Remember that intra means inside. Don't use that to the inter. That's completely different too. Then inter would be means what? In between the molecules. So I showed the example in here. Showing that we have hydrogen, it's given over here. The chlorine is given here. Guys, what's inside? Inside, we have something known as the covalent bonding. And this is something that inside, so this would be intramolecular forces between the hydrogen and chloride. But when we say inter, it would be in between another hydrogen and chloride there. If they have some sort of the interaction, okay, that's called the inter. Okay, that's later on you're gonna learn about different type of inter. This is known as the dipole-dipole interaction. So just simply remember that whenever you're asked to do answer like what the intramolecular forces, I'm simply asking you what type of bondings they're carrying. Okay, so I'm not going to talk about more about metallic and ionic because we spent so much time on that too. Let's revise that some more of the intramolecular force of the covalent bonding. That's also given over here, by the way. Okay, so, and in fact, because we're talking about molecular, more likely when we say intermolecular, it's more related to the covalent bondings more because, as I said, metals hard to get hard to achieve the molecular structure. Ionic bondings hard to achieve that. Sometimes we do, but sometimes many times we don't. Page 220, please. This table here shows you that the actual numbers, some numbers of the electronegativity trends, an extra number of those. So what you're seeing there is, you're seeing that as we're following the trends of electronegativity, that we have the greatest electronegativity in the fluorine, which is 3.98, almost like a 4, lowest at francium, 0.7. So that tells you that the tendency of gaining electrons is getting stronger going into this order. Does it make sense up to here? Now, why are we given this quantitative numbers too? Because we're going to actually think about the differences here. So if we have a combination of hydrogen, when hydrogen and fluorine goes like this. Hydrogen carries the electronegativity of the 2.20. Fluorine carries the electronegativity of the 4, almost like 3.98. So I'll make it like almost a 4, but let's write it, follow the exact value. 2.2, 3.98. This means that hydrogen carries that much of the strength of the attracting the electrons, and fluorine has 3.98, much greater, 1.5 times almost like that too. Okay, so let us think about what happens in between these two when they have significant difference of the electronegativity. Oh, by the way, I'm not talking about fluorine to those metals because this is basically forming the ionic bonding straight away. Means having lower electronegativity means they're just willing to give away the electrons. But hydrogen, the way we can interpret hydrogen's electronegativity is, it still wants to get the electron. In other words, hydrogen doesn't like to. Does not like to. So like to lose electron from the number given 2.20. Okay, so let us think about what happened when the hydrogens are forming a bond with this same hydrogen. Okay, what is hydrogen? It's made of. Hydrogen is simply made with 1 proton. From the atomic number 1, mass number 1. No neutron at all too. So when the electron is orbiting with the 1 hydrogen, it will be something look like this. And I will hope you to remember, like imagine that the reason why electron is something that moving around the proton is it's neutralizing. Electron is neutralizing the positively charged. Neutralizing as in what? Making 0 And this is something that's very important in chemistry, that we always need to understand that plus and negative, they attract to each other. And then they like to neutralize to each other. We learned it from the ionic bondings, that they love to attach so that they can neutralize it. Same things happen to this hydrogen. I showed a different color. It was orbiting like this. So before they decide to form the covalent bondings, what they do, electrons for each side, it's a kind of orbiting or kind of moving around and equally neutralizing the positive charge of the hydrogen nucleus. Okay, that's what happened before. Now, when they decided to share, forming the covalent bonding, this is what happened then. As they they found the necessity to form the covalent bondings. What they do, this covalent bonding in the purple will now go cross. Okay, and as if they are a little bit of a single bridge. And the blue, the green will also go to cross. So what you start seeing here is there will be a equal share of the electrons. And where is that coming from? Where is the equal shares coming out from? Because both of the hydrogen carries the electronegativity, same tendency, same amount of the 2.2 electronegativity. So they have equal power, which means if I take one, I need to take one from that too. That's the kind of rule that we have to remember. If they have an equal power, equal electronegativity, they will equally share the electrons too. For the carbon and hydrogen, it will be something that's very similar. Carbon carries the electronegativity to 2.55, which is slightly higher than the hydrogen. So, but we tend to say they have a very similar electronegativity. So what they do with the hydrogens, electron will be kind of shared equally too. Or you can say it's more like carbon's a little more stronger too, but it's kind of negligible in this case. But the problem starts when we have a combination of hydrogen, let's say for fluorine. Let's bring that again. Okay. Fluorine has the electronegativity of the 3.98, whereas hydrogen has 2.2. So let's draw that, the purple and green again. Assume that they are having a blue, the green and the purple. Before they forming the covalent bonding, these used to kind of hanging around. So instead of drawing the hydrogen, I probably just draw the proton inside here like this. It's the same thing. Now, before they're forming bonding, yes, equally sharing the electrons. Good, good. Okay. Now, let's see what happened between these two when they decided to forming a covalent bonding, or when they decided to share the electrons. As we discussed, fluorine carries the super electronegativity, the strongest electronegativity. And the meaning of electronegativity is that it's a tendency of the gaining electron, or tendency of the pulling electrons towards to its side. Does it make sense? So this is what happened then. This purple electron that used to belong to hydrogen will no longer be reaching to it. So this is shared, they're saying, but it's kind of hanging around in this region only. What you see there is, this side will be partially neutralizing the positive, but that side, that's a no neutralizing or neutralization at all. So enlarge that, you will see the plus of the hydrogen. We only receive the electron hanging on this side here. There'll be no electrons outside here. So you will see only the parts of that get neutralized. And this side will be not neutralized. And considering the meaning of the not neutralized, that this side, I call that as, this side started getting them partially positive. Okay, what about for fluorine side there too? It's almost look like fluorine attain that electron, but it's not a complete like a gain of the electron, because still remember that hydrogen carries a relatively high electronegativity compared to other elements. It doesn't like to lose electron at all. So what they do is kind of holding. This is how I describe it. Hydrogen is kind of holding that, the last cover, like the last string that. So it doesn't let go. So for the fluorine side, it's not a complete gain of the electron. It's more like a partial gain, almost like 80%, 90%, but still, it's not a complete. So what they do is the partial, the gaining of the electron, which makes that to be partially negative. Remember the meaning of the partially. It's not a complete +1 and ±1. It'll be something like quantitatively like 0.8, 0.7 minus, but I don't like to use the 0.7 every single time. I just simply say it's a partially, okay? The way we can describe the partial positive and partial negative is, in some cases, we're using that delta, okay? Delta means a difference between one to another. We use commonly delta positive, delta negative like this. But instead of using the triangle, you'll probably start to see that the delta as in a D of the Latin positive or D of the negative like this. Then this means that there will be some partial charges of positive and negative. So this is how we can also describe that in the arrows, in the positive, we're moving from positive to the negative goes in this order. Which means it will now having the partial positive and negative, carrying some partial positive and negative. But does that mean that this is not a covalent bonding? Does that mean like it'd be like ionic bonding then? No, I cannot say the ionic bonding. Remember, the ionic bonding means complete transfer, complete gaining, complete lost. This is not a completed yet. So I can still say this is a what? The bonding between that is still be a covalent bonding, as they're sharing the electrons yet, but because they're starting to having some positive and negative, this is known as polar covalent bonding. It's a new type of the inside bondings that you need to remember. So polar covalent bonding is due to what? It's known as from the equal share of the electrons due to significant electronegativity differences. In other words, when we have equal share of the electrons, this is now named as non-polar covalent bonding then. Okay, so now we learned the two different, the special type of the covalent bonding. One is polar, one is non-polar. Remember that when they have a really strong, significant difference of the electronegativity, yes, they started having some polar and non-polar too. Does it make sense? Now, from here, what you can see there is we have plus and minus. We have plus and minus there. So how many polarities that we have in here? We have plus and minus, we have two polarities. So I call that this situation as, this is a dipole. So hydrogen fluoride, now we tend to say that as, is now having that dipole. Just try to, you don't have to understand anything in here, just try to accept that as, oh, okay, we got two polarities. It means two charges. One is positive, one is negative. And now having one dipole carried by the hydrogen fluoride. Does it make sense? I'm still talking about what happens inside. I haven't touched the outside, like in between the molecules. Everyone good? Okay? All right. So when do we know they're having the polar covalent bondings and non-polar covalent bondings? Okay, the standard for deciding that is, okay, one thing, you do not need to memorize any of these values. Don't bother to. Why should you? Okay, but what you need to know is Hydrogen among the non-metals has the lowest electronegativity. Okay, fluorine, oxygen, nitrogen carries the highest. So they are the highest. Yes, what about the chlorine? Yeah, compared to the oxygen, chlorine has relatively lower electronegativity. So that would be probably, you can think of an effect of the moving across the period has a greater effect than moving down the group in terms of the increase in the electronegativity. So we only consider about group 2, sorry, the period 2, these two are known to be the strongest. So having the strongest electronegativity means you can interpret that as this. When these three, when nitrogen, oxygen, fluorine share the electron with the hydrogen, okay, this means that there will be the greatest, there'll be greatest the dipole created or generated. Again, dipole means that partial positive and partial negative, because they have this significant, the most important, again, the most significant like difference between one to another, means that you have a greater positive and negative in our form too. Okay, simply, we just got to determine that electronegativity. So, non-polar covalent bonds is given on your page 220. A non-polar covalent bond is formed between the same atoms and atoms with a very similar electronegativity. So, quantitatively, the difference in the electronegativity between bonded atoms is less than 0.5. When they have a difference in the electronegativity that's less than 4.5, we tend to say they're non-polar. They are equally sharing the electrons in this case. And this is the reason why carbon and hydrogen, which has 2.55 and 2.20, difference of them is only 0.3, they would have the non-polar covalent bonding in that reason. Does it make sense? Okay. Same for that. Oxygen to oxygen, if they form that too, there will be non-polar covalent bondings. What about nitrogen to hydrogen then? It'll be greater than 0.5 differences too. It means nitrogen carries 3.04, hydrogen has 2.2, so the difference would be 0.8, greater than 0.5. They started forming something known as non-polar covalent bonding in their case. So page 221 shows you that what happens when the electronegativity differences are from 0 to 4. So when we have a 0, it'll be non-polar bondings. Polar bonding between from 0.5, from polar bonds to 1.7. So as a rule of thumb, electronegativity difference of the 1.7 is often used as the cutoff point between the polar covalent bondings and ionic bondings. So when something like electronegativity difference is over 1.7, it's no longer be a polar covalent bonding, which means they're not really sharing. They will be transferring electron to the metal side. So that's 1.7, kind of standard. Okay, but remember that 0.5, below 0.5 is known as the non-polar covalent bonding. Above 0.5 would be polar covalent bonding. But as I said, you do not need to memorize those numbers because you won't be given. Sometimes you do in the scientific skills, but most likely you won't be given that. You're not asked to memorize the electronegativity yet. Important to remember, just understand that as hydrogen carries the lowest electronegativity, and therefore, when it's combined with the forming covalent bonding with those high electronegative non-metals, more likely they form the polar covalent bonding, or more likely generating the dipole. Does it make sense to all? Okay, so 6.2, let's have a think about this situation here. So we're given some formulas. Let's talk about whether they are symmetrical or asymmetrical. Therefore, we can think about their joints, what they are joint with. So whether you decided that whether they came in polar or non-polar. So carbon dioxide structural formula would be carbon dioxide like this. Okay. Now what you see there is this is the symmetrical shape. Carbon, the linear shape. This is also known to be asymmetrical. And what you see there is there will be some charges. So I would consider about the relation between carbon and oxygen. Carbon and oxygen. that oxygen carries the greater electronegativity than carbon, which make a difference more greater than 0.5, means that this makes some dipole. There will be a dipole generated. So in this case, it'll be a polar. Okay, now what about the carbon dioxide? It has, yes, there are charges, partial negative, partial positive, partial negative there too. What actually happened here is, because the shape is symmetrical, which means that the equal pooling of the oxygen toward the carbons, it makes the kind of canceling the charges in this case. Inside, there will be some charges inside, but that's known to be a non-polar shape, therefore, in terms of shape. And this is some kind of controversial, by the way, because it's not sometimes depends on the shape. It depends on what their chemicals combine with. They will decide the polarities as well too. For example, tetrafluoromethane, it looks like this. As you know, fluorine carries the greatest electronegativity compared to the carbon. It's much greater. So this is a symmetrical shape because it's tetrahedral, but still it will have some polar characteristics. Now, compared it to the methane, what about this one? This is a symmetrical shape, okay? But as we discussed, carbon and hydrogen carries a very similar electronegativity. So they would not have any symmetrical, but it will be non-polar shape in this case. Does it make sense? Okay. So sometimes it's really important to know what's attached to it, especially in the organic chemistry later on. Water has OH. Okay, this is clear that this is asymmetrical shape, as well as we have attachment of the oxygen to the hydrogen. Therefore, it carries the greatest, one of the greatest dipole. This is a polar shape. Ammonia, NH3, shape of the trigonal pyramidals. This is asymmetrical. Okay. Also, in between the nitrogen and the hydrogen, it carries a huge amount of a huge difference of the electronegativity. So it would be polar in that reason. Okay. So two things you have to consider. One, do you look at the shape through the VSEPR theory, say that whether the shape is symmetrical or asymmetrical? If the shape is asymmetrical, more likely the shape will induce the polarities. Okay, there are some exceptions, by the way, but two, you look at what chemical composition of that too. If you see that great difference of the electronegativity between one to another, more likely they are having some polarities or dipoles in this case. And that's something that's very important later on too, because carrying the polarities, carrying some dipole, will decide their physical property. For example, we have a CO2. Let's bring it up. CO2 that look like this is known as non-polar. We have a H2O that's known as polar. Okay, now it's kind of interesting that I just described that hydrogen and carbon has similar electronegativity. So it has oxygen attached to oxygen attached to. So they look very similar in terms of the structure and the composition too. But one is known as polar and non-polar because of the shape, bent. One is linear. Now, I want you to think about CO2 in the everyday life. When we say CO2, carbon dioxide, in the room temperature, that comes out in what? The gas state. What about this? This comes in liquid. We get liquid water. Okay? Then, what makes them, even though they look very similar, what makes them to be in the state of the gas? What makes them state in the liquid? In other words, in terms of the boiling point, having comes out in the gaseous state means that CO2 has really low boiling point. It's already been boiled at 25. This has a boiling point of 100, high 100 degrees Celsius too. What makes them to have the physical property of the 100 degrees Celsius high boiling point compared to this? As you can see the difference here, only difference between these two is whether there's a polar or non-polar. Means that carrying something polarities will decide their interactions between the two. So that is known as the intermolecular forces. Okay, so let's bring it out again. So intermolecular forces. Again, in between the molecules to the molecules. So what we have there is, let's bring that here. O and H. Oxygen and hydrogen, as you can see, like they have a huge electronegativity differences too, which means that this makes hydrogen to be partially positive, pulling the electrons, and there'll be two partial positives from the one oxygen attached. They'll be partially negative like this. Okay, again, this is dipole. I call that a dipole. Does it make sense though here? Okay, we have a dipole, and I'm talking about these as a polar covalent bonding, which is an inside of the oxygen-hydrogen relationship. Okay, let's bring it out another water molecules. This will be the identical, so they're partially negative, partially positive. Now, what you have to remember is something that positive will always attract something that negative. This is the nature of the law of the nature, which means these two will be, there will be attraction due to the positive, due to the charges, due to the partial charges. I'm not talking about like inside now. I'm talking about one water molecule to another water molecules. They are now started getting attracted. On the other side there too, we have another oxygen and hydrogen that will be joined, and there will be some hydrogen will be on the top to two. So you will see like that's kind of network in here. It doesn't make a lattice there. Many of those can be joined because they have carry some partial positive and negative. And what you started seeing here is you're seeing that this is attraction and this is another dipole. So what we have is we have a one dipole from oxygen to hydrogen, another dipole from another water molecules there too. So this interaction is called because it's the interaction between dipole to another dipole, it's actually known as dipole-dipole interaction. Does it make sense? Okay. Dipole-dipole interaction. This means that this is now I'm talking about intermolecular forces. This is in between two or more molecules now. Okay. But what makes the dipole-dipole interaction? Where should we start it from? We should have started from the electronegativity, therefore forming some polar covalent bonding. So having the polar covalent bonding in intra would induce to them to have some dipole-dipole interactions at the inter. Does it make sense to all? Okay, just try to picture that as intra means always being inside, inter means always in between. Now, we have that situation. So this explains you why. Let's draw the CO2. Let's bring that in here. Yes, there will be some dipoles there, partial negative, partial positive, negative, negative, and positive there too. Now, compared to the water side of here, because, okay, this is why the shape is sometimes very important. When I can see the dipoles of the carbon and oxygen, okay, there's no doubt. They'll be like, yeah, there'll be a dipole. But because of the shape, when this carbon is trying to attach to the oxygen, just think about here. This is basically a carbon. I showed the realistic, like carbon is surrounded by the two oxygens like this. Okay, and this is a linear shape. I have another carbon, oxygen, and oxygen. What we try to do is we try to attach these if we want to get the dipole-dipole interaction. But what happened is because oxygen is partial negative, this is partial negative, they will repel, make a repulsive force to each other. This is why having the bent shape, asymmetrical shape is something very beneficial. It's kind of tinted out so that it can joint easily. So what that make is that they will not joint or they're not really interacting as of the water molecules like this. So this is the reason why Carbon dioxide in a linear shape and the nonpolar comes in a gaseous state. Because once you can think about it here. When two carbon that comes along, because of repulsive force, they kind of repel each other. They would not be attached. Water molecules, however, as kind of bent shape, they would love to come to and feel building up. This is why they come to liquid and more flexible too. This is free to go. Does it make sense to all? Okay. So carbon dioxide, it doesn't mean like it do not have any other interactions. No. If you think about it in here, there will be out of millions, out of trillion, there will be some cases that carbon is successfully attached to the oxygen. Because we have a trillion. So you think about a little bit of probability. But that would be really temporarily. Because these two oxygens are like, hey, what are you doing? Go away. Straight away. So what that makes is, we call that as temporally dipole. So they will be having some temporal dipole. Okay, which is temporally, it just doesn't go for like a second or something milliseconds. We could describe that interaction as dispersion force. Sometimes known as London dispersion or London force, but dispersion force is a typical names we use in year 11, year 12 syllabus for the HSA. So please remember that I'm still talking about the intermolecular forces, not the intra anymore. Okay, so there are typically two types of the interaction. One is due to that dipole, which is known as dipole-dipole interaction. Two is known about temporal the interaction, temporal like a polar and non-polar, called the dispersion force. So comparing the magnitude then, what we can imagine is, because this is more efficient in terms of the attracting to each other, this is much greater. Okay, means to break the bond, to break the interaction between two, to separate them, I need to work harder. This is why it has shown on the high boiling point. I don't need to do anything with CO2. It's been separated in the gaseous state. Does it make sense? Can you picture that? As I said, I can bring that again to the module 7 organic chemistry about COOH again too. It has carbon and oxygen and hydrogen. Then you got to think about the relation in there too. That when some of those will carry now dipoles, therefore have a greater greater interaction. So some of the alcohol in this reason, OH attached, methanol, ethanol especially, like if somebody drinking alcohol, that comes in liquid state. Okay, CH4, methane. Have you heard about methane gas or butane gas even too? That comes in gaseous state because they don't have any polarities. Dipole dispersion forces too. We were going to discuss more about it in year 12, but I'm simply covering some parts of the year 12 as well too. And this is actually, you can ask your siblings, some other people, you will get this question in HSC. They're actually asking you why let's say methane has greater boiling point than alcohol. Or let's say the lower boiling point than alcohol like this. Okay? So out of many dipole, there's one more thing. So one more. Just remember that dipole is from that intra, and interaction between two dipoles known as dipole-dipole. Now, let us consider about hydrogen again. When hydrogen forming bonding with nitrogen, oxygen, or the fluorine. As I discussed that nitrogen, oxygen, fluorine has the greatest electronegativity. So the difference between these two in terms of electronegativity would be the greatest too. So this will be the combinations of the greatest electronegativity. Differences. What we do is we ignore the chlorine. Yes, it has it's greater than the nitrogen in terms of electronegativity, but because they're in the down under the period, we kind of ignore that in this case. We only consider about period 2. Okay. Okay, this means we can reinterpret that as it has the greatest greatest dipole magnitude. Carrying the greatest dipole magnitude means that it just simply means that it's a greater, stronger positive, stronger negative. So stronger partial positive and partial negative in this case. So compared to other dipoles, or you're thinking about the combination between those, this dipole, these dipole interaction then will be the strongest out of many. So let's think about what it means like having the strongest interaction or attraction. It means they're almost like, okay, showing the two molecules, if there was some intermolecular forces, they're kind of attaching to each other, attracting to each other. But if the attraction is strong enough, this is what happened. They'll be attached. Okay, it looked like they form some sort of a bonding, isn't it? Okay, what is the bonding inducing to? Bring back the water. We have OH and H. It means O and H is almost like attached. Okay, it looked like they are forming some sort of the bondings again too. So this is the reason why we give a special name for this type of dipole that is known as hydrogen bonding. It's simply because this is the strongest out of the many dipoles. Remember that this is the special dipole, and this is not an intramolecular. Even though we have a name of bondings, the bonding name comes out from because they are strongest. They are so strong that it will kind of bond it. It doesn't mean that they're intra. Okay? So don't get confused because I see so many students writing that hydrogen bonding is the strongest intramolecular forces. I was like, don't do it, okay? No. Remember that intra is talking about inside. I'm not talking about inside. Intra, what about intramolecular force then? Actually, what about intramolecular force in this case? What covalent? Would it be a polar or non-polar? What would be intramolecular force of this situation here? It would be polar. Covalent bonding then. Okay, don't get confused about these 2 points. I know this is why it will bother you a lot. And I need to reuse the contents when we're talking about solubility later on too. And this is the reason why ionic compounds get dissolved into water. Because water carries lots of the partial positive and negative, it will help them to neutralize partial charges of the ions, separating them too. Okay, but without understanding the intramolecular, especially intra and to the intermolecular force relationship, see that you can't do well in your molecular, organic chemistry without this. You can't do well in the solubility, which is module 5 of the year 12. We're going to learn about solubility in detail with the calculations, but without that, good luck. Okay, so you're missing two modules without this one, and definitely you get a HEC questions related to that too. Not only for that, year 11, you may get a question about what the intramolecular force is in this case. But does it make sense? I'll try to give you some big pictures of intramolecular forces. So let's summarize that. What type of the intra that we would have? It's given on your workbook. Yeah, don't worry about this one for now. We talked about lots of these. Page 228, it shows you that type of the intermolecular force that we have dipole attraction or dipole interaction, same thing. And occurs between the partial opposite charges ions, and relatively this is strong. Hydrogen bonding, hydrogen atoms with oxygen, nitrogen, fluorine only too, means that this is the strongest and a very special type of the. Remember that bond doesn't mean like intra, it means inter, between oxygen to the hydrogen or oxygen to the other things, or nitrogen, fluorine. London dispersion, or sometimes known as dispersion force, is temporarily charged. Remember the carbon dioxide? Yes, carbon successfully attached to oxygen, but the other oxygen kind of pulling away. So temporarily. So that's the weakest out of the three. We only have three. We have only two actually, of the intermolecular forces. Don't bring it out something else. Don't bring it like some sort of like a random carbon forces whatsoever. Okay, we only have a two, which is dipole-dipole, which is polar, or the dispersion non-polar more likely, or the temporarily polar. Out of the inside of the dipole-dipole, we have a special type of the dipole, which is hydrogen bonding only. Make sense? Okay. All right. Shall we try this question then? Page 229, please. I would like to answer that question. I'll give you about 3 minutes for this. Can you see that, Christine? Yeah. Where is it from? What produced that kind of force? So giving an answer for dispersion force, that's a temporarily dipole. Yep. Well, and you can answer for the dipole then. Okay. Out of many year 11 chemistry class or lessons, I picked Intra is one of the most important. Vector theory is okay. Like, I mean, you just simply need to know how to do it. But this is definitely that all related to the year 12. Yeah, and I would not like spend too much time on the Schrödinger's model too, because you only get 1 or 2 questions about it. So I will explain you how to deal with those type of questions, school exam questions, rather than why the Schrödinger models explain your orbital models and stuff like that too. So it's more like a shortcut to save your time. Okay, almost finished. Okay, where can we find the dispersion forces? Where is something important? Dispersion force is known to be an intermolecular forces, so in between. So okay, intermolecular or in between. In between which one? In between the non-polar to non-polar. Sometimes be non-polar to the polar too, but because they don't have any charges in this case. Origin is from the temporal dipole, and the relative strength of that is this is the weak. I mean, probably the weakest out of the many of the forces that we're talking about. Dipole forces generated from is intermolecular between intermolecular in polar to polar. So origin would be, where is it from? It's from that dipoles due to the electronegativity difference. If they have electronegative differences greater than 0.5, we tend to say, so simply say polar covalent bonding. I'm happy to see that too. Relative strengths, relatively strong compared to the dispersion force. Hydrogen bonds, don't remember that. I know, like after, if you come back in a week, and if you don't revise that this week or next week, or like more like it today, you're probably saying this is intra by looking at the bondings. But make sure you answer that as this is intermolecular between hydrogen 2, oxygen, nitrogen, and fluorine. Okay, where is it from? This is the strongest, from the strongest dipole from the hydrogen 2, that 2, or that's from polar covalent bonding. Covalent bonding there. And this is known to be what? Strongest out of many of those. Covalent bonds is something that's quite different to it. This is intra, in between what? Non-metals plus non-metals. Origin is where, how is it formed? It's by sharing the valence electrons. Okay, it always must be the valence electrons. Relative strength. Okay, covalent bonding. If you compare the intramolecular force than intermolecular force, I want you to think about it in here. Like, I'm talking about breaking this bonding between two, compared it to separating these two. Which would be harder, separation or the complete destruction? It would be much easier to separate them too. Okay, I mean, it takes harder and much more effort to break this, okay, rather than attached, now separated. So compared to all other intermolecular forces, intramolecular forces known to be stronger. So it would be stronger than, generally stronger than, and any other like intermolecular force. Molecular. Same for the metallic bonding, guys. Okay, it's even though like we say the metal is like, I want you to think of like separating the metals to metals. That's actually harder than boiling water, isn't it? Okay, any bonding street. If you want to separate the sodium ion separately from the chloride, other things, it's much easier, much harder. So that's something that you must remember, that in the difference between inter. I spent quite a lot of time with the bondings and some revisions too, but don't forget about VSEPR theory, basic structures, 2, 3, 4, linear, trigonal planar, tetrahedral, and how to do that, including lone pairs, and then determine the shape, and inter and intramolecular forces. So I covered quite a lot of detail on the contents because I wanted to revise some of the contents and move on to that, because I can see there's a close relationship between bondings that we learned last year. It was last year, by the way, okay, last term, and up to here. Any questions? If you don't, that's it for today. Homework, yes. Homework is now uploaded on the Google, the class 365. You can download that too, but for those people who cannot come to the offline, but for